We talked about how we could describe the position of an object on a coordinate axis in a coordinate system, and we talked about how we could measure its displacement and see how far the object moves. But we really need to take that to another level to say that we don't only care where the object is, its position. We don't only care how far it's moved and what direction, that's its displacement. But if we want to know how fast the object's moving, we need to know how far it travels and also how fast it's traveling. And the way that we describe how fast the object is traveling is through the velocity. The velocity is measuring the object's position's rate of change at a fixed instant. A rate of change at an instant is a time derivative. So our instantaneous velocity is the time derivative of the position. It's telling us how fast that object is going and in what direction at a certain instant of time when the object is at a certain position. Notice that the velocity being the time derivative of position is the default assumption. So when you omit instantaneous, it's assumed that you're finding the velocity at an instant. When the derivative shows up as the slope of the tangent line in a position versus time graph, if we are differentiating that position function. If the derivative is negative, that means that the position is going from a bigger value of x to a smaller value of x. That means it's going from farther from the origin, farther to the right of the origin, back closer to the origin, back to the left. And so a negative velocity means leftward motion. A positive velocity means that you're getting farther and farther to the right of the origin, which means you're moving to the right in that case. The magnitude of the instantaneous velocity is the instantaneous speed. The magnitude of the velocity vector and the magnitude of every vector is always positive. It's basically the absolute value of the velocity that we have. That tells you your instantaneous speed. That's telling you how fast you're going at the instant. And then the sign, whether this velocity is plus or minus, is going to tell you the direction of travel. If velocity is positive, we're going to the right. And if it's negative, it means we're moving to the left. Those are our standard convention to use to distinguish that direction. The derivative is the slope of the tangent line. If you have a graph, this is our instantaneous velocity, is the slope of the tangent line to our position graph. Or if we have a position function, we can take a derivative using the normal rules of calculus. Position is measured in meters. dt, time, is measured in seconds. And so our velocity is measured in meters per second. How many meters the object has moved per second of motion is our SI system, or feet per second as the base unit in the imperial system. If we want to find the average velocity is looking at the rate of change of the position. It's looking at the displacement, how far we've gone during a finite time interval. That's what this average part means. Instantaneous means at an instant during a differential time interval, a infinitesimally small time interval. The average value means over a finite time interval, delta t. What it means to be a finite time interval could be 1 second, it could be 5 seconds, it could be 10 hours, but it's definitely finite compared to the infinitely small time interval dt. So our average velocity can be found looking at the total displacement over the total time that elapses during this interval. This delta x over delta t ends up looking like x2 minus x1 over t2 minus t1. This is a slope. That's the slope equation. And in fact, our average velocity is a slope on a position versus time graph. It's not the slope of a tangent line, but it's the slope between these 2 points, t1x1 and t2x2. It's the slope of the secant line. The slope of a secant line on the position graph shows you the average velocity between these 2 points. Sometimes the velocity is positive and faster. Sometimes the velocity is negative. The average velocity during this entire time interval is the slope of that line. It's also possible to have a velocity versus time graph. And if you have the velocity versus time graph, you can also find the average velocity by integrating that velocity graph integrating the velocity function, dividing by the width of the interval gives you the average velocity across that interval. This is the exact same equation we saw for average position. This is the average value theorem. And in either case, these are average values of the velocity, but our units are going to be the same as instantaneous velocity. They're going to be meters per second or feet per second. Another thing that we need to consider is average speed. Average speed is related to average velocity, but it's a little bit different. Average velocity, we saw, was displacement per time. Remember that displacement is a vector quantity where we look at just the distance between the endpoints, and we can make it plus or minus based on the direction. Average speed is the distance traveled per time. And so our average speed is, I use just a S with a line over the top, a bar over the top. This is a statistics nomenclature to say the average value of the speed is the total distance traveled divided by the total time. We've already talked about how to find the total distance using a graph or using a motion diagram. Find out how long it takes, the total time that it takes to undergo that total distance, and you'll find the average speed. The total distance should always be positive, so the average speed is always going to be positive, and it is going to be measured in meters per second or feet per second as well. Average speed is another one of those more practical applications. It's not really very scientific, but it's used a lot in sort of real-life calculations. And lastly, we said that our velocity is the derivative of position. That was our definition. So if we have position, we can take the derivative to find the velocity, but we should be able to undo that as well. We should be able to reverse that relationship. If velocity is the time derivative of position, then position should be the antiderivative of velocity, kind of. The thing is, whenever you do a integral, you always get a plus c. And so that's going to require an initial condition. You need to know your starting point so that you can figure out where you are later on. Basically, what's happening is your velocity is telling you how fast you're going and what direction you're going in. And so if you do an integral, you can figure out how fast you have been going and in what direction you have been going in. But you always need a starting point so that you can build on that starting point plus the distance traveled to tell you where you're going to end up being. So if you have a velocity function, you can take the integral to find the position function, but you need it to know an initial condition, an initial position at some initial point in time to find the value of this plus c. Or if you do a definite integral, the definite integral does not give you position. The definite integral gives you the displacement, because what this function is this is the velocity. This is how fast you're going times the time is the displacement, the little bitty distance dx that you've traveled. When you add up all the little bitty dx's, it gives you the total displacement that you've undergone. But again, you would have to know an initial condition to add this displacement to figure out where you started from. Last thing to point out here, notice that if you divide both sides by delta t, this quantity here is the average velocity. And this takes us back to our average value theorem. This is how you'd find the average velocity also. So we can see how those two definitions of average velocity are related to one another. These two definitions that we saw here are related by this definition and really through the original definition for velocity.